Anyone wants to say anything about this? Have you come across sample size calculation problems?
As in, like, not sufficient sample size, is it?
Well, okay, so you do know about, so when you do an experiment, right? So one of the questions that you would like to ask is how big should your sample size be, right? So how do you answer that question in a statistical context?
I have no idea about this.
Anyone else wants to have something to say? So you do an experiment. This is the kind of problem that you might get asked as a consultant, right? So the person wants to ask you, so how big should my study be? Should I collect sample size of 100, 200, 500, or more, or less? Because sample size equals to cost, yeah? So ideally, you do not want to, you want to control the cost of the study around certain kinds of amount. So because you don't have infinite resource and you don't have infinite time, right? Because collecting samples take time and money, okay? So usually that's why you have to make some decision about what's a reasonable sample size for your study. This is the kind of problem that people will ask. Usually they will ask statisticians, hopefully at the beginning of their project. And that is the correct way to do it. Because after the project is done, then there's no point asking this question because it's already a done deal, right? So today later, this person will actually talk about her problem. So it's kind of like you could say that it's like some kind of consulting session, right? So consulting sessions. So you in this kind of sessions, you actually hear about a problem where the subject matter may be very new to you, right? And you may not have actually come across it. That's very normal. But what the consultant does is that the consultant actually asks questions and try to learn about the problem. Learn enough about the problem to actually formulate it in terms of a statistical problem, right? And that's if you're able to get to that stage, then you will be able to offer a solution. Okay, so this is one of the things. Okay, so we're going to have some real world experience later. And just to share a bit about my experience with this sort of issues like sample size calculation. In the real world, I would say sample size calculation may be a little bit overrated. In fact, I would say that most of the time, in the consulting setting, the primary determinant of the sample size is basically how much money the client actually is willing to spend, okay, on the sample size. Because there's actually no point if the client is not willing to spend more than a certain amount, then there's no point making calculations that tell him that you need to get this sample size because he's not willing to go to that stage. So a lot of times it actually turns out that sample size kind of advice is basically, although it's good to have some calculations, right? And you do need to know statistical theory in order to be able to make that calculation. But in practice, I find that a lot of times the answer is actually just you just need to ask the client roughly how much, what is the cost per sample, and how much you're willing to put on that, and that's it. And then you can easily figure out the sample size, and then that's that. And then you can just go ahead and do your statistical analysis. Okay. Of course, the danger in that kind of work is that if you also need to advise the client that, of course, you can just use this simple approach, right? Just get as many samples as your budget allows, your budget and your time allows. But at the same time, if he's actually looking at some kind of uncertainty, degree of uncertainty that is of a certain level, right, small enough, then you have to warn him that even if, with this budget, you are not able to achieve that. So whether that's something that he wants to go ahead or not, right? So there are two aspects that you can actually offer. Yeah, they will offer different perspectives to the client about this sample size calculations. Okay, so yeah, so I'll put here the very simple approach is take as many samples as possible, under budget and time constraint. Okay, and ask if there's any desired degree of uncertainty, right? That must be attained. So, okay, and you can actually warn the client that the sample size that's allowed under his budget is actually not going to answer this part, and that may so the client may actually, if this part is very important, then the client may need to either get more money for the project or basically just abandon the project. All right, because if they go ahead, there's no way this degree of uncertainty can be actually satisfied. Now, degree of uncertainty is actually related to the standard error of your parameter estimate, right? Okay, so if the degree of uncertainty is high, then the standard error will be high, and if the degree of uncertainty is low, then correspondingly your SE is actually low, right? So the more sophisticated approach will be to actually a formal analysis, right? You can do a formal analysis. And there are actually two ways to do this. One is the so-called power analysis. And the other one is controlling for margin of error. Okay, so the very common one that academicians will ask will be this one, power analysis. Whereas controlling for margin of error, maybe you may get more people from industry who ask you. Right? So actually, personally, I think that number two actually makes it's actually contextually it actually makes more sense than doing power analysis. But power analysis has some kind of a grip on a lot of people to the extent that when they ask for sample size calculation, they always try to think of it in terms of power analysis. From my perspective, actually, it is actually not that useful. But doing the second approach is something that is more meaningful. Okay, so I'll show you why I have this kind of thought. All right, so before that, so we will go through some theory. Yeah, go through a bit of theory so that you have some idea about the theory. Okay. So any questions so far?
No.
Do you know? Okay, so before that, I just want to check on everyone. Do you know what is statistical power? This power analysis, this power here means statistical power. Basically, it means the power of a statistical test. So power is actually a technical term. Yeah, it doesn't mean that there is a precise definition for technical definition for power. So are there people here who do not actually know it, what power is?
Is it the 1 minus type 2 error?
1 minus probability of type 2 error. Yes, it is. But then it has actually it's actually a kind of probability, yeah, that's associated with hypothesis test. So if you have, I know some of you actually don't come from a statistics background, so you may not actually know a lot about statistical inference. So you may need to actually do a lot of, you may need to do some personal reading on that. If you're taking stats inference this semester, then you actually will come across that, right? So, but then we cannot be covering that kind of thing in this, because it's considered an undergraduate kind of level kind of understanding. So for those who may not have come with this part, so you may have to do a bit of self-study, yeah, to cover. Okay. All right. Okay. So let me talk about power calculation using a simple example. Okay. So I'm going to start with. So you have a scientific question. You start with a scientific question, right? So like scientific question, I'll start with something that is very simple. So you have this coin here. This is a coin, yeah. So your question is this coin biased towards head? All right. So you can ask a question like this. So is this coin biased towards head? Which means it tends to give heads more often than tails. Yeah. So that in other words, the probability of actually getting a hit for this coin when you toss it is actually higher. All right. Okay. So when you have a question like this, you can formulate it. You can. This is basically in in layman's term, right? So everyone can ask this question. Anyone can ask this question. Right? This is coin bias. And then you have to formulate the question in statistical terms. So how do you do this, right? So you formulate this in statistical terms. That means you have to introduce parameters. Introduce parameters. So what parameter will be relevant for this problem? So the parameter will be, let's say, theta, which is the probability of a hit, right? Assuming it is fair. Okay, now, so the probability of this coin, right, being turning up a head actually will depend on your assumptions, right? Now, in a very, so in hypothesis testing, we rely on the concept of falsification to prove a point, right? You cannot directly prove something, but you can use falsification to argue for your case. So if you want to show evidence that the coin is biased, right? So you will make the assumption that the coin is fair, okay? And then your alternative, in fact, this is actually your so-called null hypothesis, right? And your alternative hypothesis is that the coin is not fair, right? It could be something else. Not fair is very general, right? You could say that it is biased towards head or biased towards tail, right? Now these are verbal descriptions, but you can actually express this in terms of related to the parameter. So here, this parameter would be theta is equal to 1/2, right? And here will be theta is not equal to 1/2. Okay. All right. So far, so good. Everyone.
Okay for me.
All right. Now, so once you have this null hypothesis and all that, so you will construct what you call a test statistic, right? So this test statistic is basically some kind of a function, right? This is a function of the data, okay? Whereby you can use it to make a decision about whether you want to reject the null hypothesis or not, right? And this test statistic has a distribution, okay? So this function of data here that you use, actually it has a distribution. And because why does it have a distribution? Because every time you toss the coin a certain number of times, right, you will get different results, okay? And if you collect those results, if you repeat this experiment multiple times and you collect those results, you plot them, you will get a histogram, all right? So that would be the distribution of the test statistic under the null hypothesis, okay? But of course, this can be worked out theoretically if certain assumptions about the data distribution is met, okay? So in this case, the test statistic that is associated with this testing this problem has this form. So you have first, you can have theta hat, which is basically the observed relative frequency, right, of hit, okay? So basically, this is the number of hits over the n, right? N is the sample size, right? How many times you toss the coin. Okay, so this is actually a function of the data, yeah? This is what we call a statistic, This statistic has no S, yeah? Okay, so this statistic means some function of the data. Okay, so your data is here, yeah? You can count how many, you toss the coin, you count how many times the head appears. So this is a statistic. Now, it is known that if your n is sufficiently large, so assumption here, if n is large enough, so we leave large enough undefined, okay? Just that if n is sufficiently large, then your relative frequency here would have an approximate normal distribution with mean theta, and variance equal to this. Okay, so who can tell me why the distribution of theta hat is approximately normal with these parameters? It's invoked. What sort of result is being invoked here? I know quite many of you took the probability theory last semester. Can anyone relate? What law is it?
Is it central limit theorem?
Central limit theorem. What do you think? Everyone else? Is it based on the central limit theorem?
I think it's based on law of large number.
Law of large number, central limit theorem. Anyone else? So you know that, so okay, so this is basically central limit theorem, yeah. But of course, how you get these values here are based on the law of large numbers. Okay, but this result is basically central limit theorem. So the law of large numbers states that this theta hat will converge, yeah, to theta. Okay, and it's very it's talking more about the convergence result, right? So basically, and of course, you can find out the variance of this thing, right? So which is basically the variance of the number of heads over n. And because you have a binomial model, right? Because the number of heads, if you toss the coin, is a binomial model. So therefore, you get theta 1 over theta n, so n squared. So that's why you get this result. Okay. All right. Okay. So you have to know your mathematical statistics. All right. Okay. So anyway, this is the statistic that we want to work with, and since we have the central limit theorem here, so this result will lead us to something useful called the Z-test. Okay, which is your Z-test is basically, so you have this form. If you normalize it, therefore you can construct this form, right? You subtract theta and you divide by the square root of the variance. Okay, and this will be approximately normal 0, 1, right? Standard normal, agree? Correct? Because when you subtract theta, you are shifting, right? You are shifting from, so this one, the distribution is here, right? Is at theta. So when you subtract theta, you basically shift it to, you subtract, so you shift it to 0, so center at 0. So this spread here may be, is dependent on this factor. So if you divide it by the square root, yeah, so the it's a kind of scaling, so you will get a standard normal. Okay. All right. So everyone remembers this. This is the Z test, yeah. So the assumption here is that your n is large enough. So generally, if your n is around, I think 30 above, it should be okay. This result, yeah, because you're invoking okay. So because in central limit theorem, the meaning of large n is basically a little bit it's left it is not stated absolutely, right? So this is basically dependent on in a very loose way, right? But generally for practical applications, if you have n more than 30, this approximation is already very good. All right. Okay, so is that okay for everyone?
Yes.
Right, okay. Yeah? Okay. So now you have your test statistic, all right. So this is your test statistic. Z equals to theta hat minus theta over square root. So this is your Z statistic under the null hypothesis. Null hypothesis, right? So your null hypothesis, if for the fair coin is theta equals to 1/2. So basically your Z is theta hat minus this over 1/2 times 1/2. The n you can bring up. So it's basically 2 square root of n theta hat minus 1/2. All right. So this is your the distribution of your test statistic. So your test statistic is like this, and this is standard 0, 1, okay, for n large enough. Which means if you repeat this experiment, right, you toss this coin many, many times, okay? Let's say this is experiment 1. Sorry, this is experiment 1, 2, 3. Okay, you can do it 10,000 times, right? So, okay, so you fix your n, right? So n is fixed. So let's say you already fixed n. Let's say your n is 50. Every time you do this, so this would be something like I give this coin to each of you and ask you to toss it 50 times. Okay, that will simulate this experiment. And of course, each of you are going to get different estimates of theta. Some of you might get 0.41. The second person may get something like 5.2, maybe something like 4.3, and 5.5, and so on. Okay. If you collect all these values, you plot them on you will get well, actually not. This is actually not that realistic. It should be something like this. Since this is standard normal, so some of them may be like this 0.5. Because you plug in this value, I should say something like this. Okay, should be like this. Okay, let's try this again. So this is theta hat, maybe 4, 5, 6, 0, 5, 1, and so on, right? So then you can calculate your Z, right? So this, after you do the Z, this may be something like 0.2, this may be minus 0.3, this may be 1.2, this may be 0.1, and so on, right? So if you collect all these values, right, you plot them, they will look approximately like this. They will be centered around some value. Okay. They'll center around certain values, right? And if your null hypothesis is correct, if your null hypothesis is correct, it will be centered around 0, right? Because your theta hat will be very close to 1/2, and when you subtract, you will get something very close to 0. Okay. So H0 is the null hypothesis. Yeah. So when the null hypothesis is true, the distribution will be centered. So the distribution of your Z will center at 0. Okay. All right. Okay. Is that okay for everyone?
Yes.
Now, okay. Now, this is you get this distribution. Okay, this distribution is a normal 0, 0, 1 because you made this assumption. Okay, that the null hypothesis is correct. What if your null hypothesis is not correct? Okay, so this is an alternate. So this is 1/2. Your alternative is, let's say, not over 1/2. So there are many possible values for theta other than 1/2. So let's say, suppose your theta is 0.8. Okay, let's say the alternative is that let's say, suppose that the coin is actually the coin, right, actually has a probability of generating the head of 0.8. So its real distribution will actually be somewhere like here. Okay, so it will be something like this. Instead of 0.5, it actually will be something like this. Okay, so roughly it will be some distribution that is also normal. Okay, normally distributed, but it's shifted. Yeah. Okay, it's shifted to some. So the mean here is sorry. Let me see. It should be. So this will be. Okay, so this will be theta hat minus. Okay, so no, sorry, this is still 0. This is still 0.5. Okay, sorry. So your theta hat here will actually converge to theta 1 just now, which is 0.8. This one. Okay. So that's why it will actually shift by 0.3 towards the right hand side, right? If your alternative is actually larger. Okay. Now, so then you can talk about the power of the test. Okay. Now the power of the test, first you need to get the definition clear, right? So the power of the test is the probability that you reject the null hypothesis, right? Assuming that the alternative is true. Okay. So to understand this, is actually good to have a diagram like this, right? Now, rejecting null hypothesis means that when your test statistic exceeds the critical values, right? So this would be your critical values. Okay, this will be Z alpha over 2, Z minus alpha over 2. So alpha is actually your probability of type 1 error. Okay. So your rejection regions are actually these two. Okay, so critical values are here. So these are rejection regions. So anytime you see a test statistic that actually is falling in the rejection region, you will reject the null hypothesis. Right? Now, so the power is given by this definition. And supposing if you assume that your alternative is 0.8, you get this distribution. So what would be the power of the test? So the power of the test would be this region and plus this part. So, but this part is actually negligible, yeah. Okay, because the distribution is has a very weak tail towards the left in this case. So in this case, your power will actually be the area under the curve on this side. All right. Okay, so this corresponds to this region here, which means if your alternative is, if it is very far away from the null, this curve, right, would actually shift towards the right-hand side, and you will eventually get power that's very high. Okay. And that is actually easy to understand, because if the coin is extremely biased to head, let's say it turns out heads 99% of the time, so its difference from the null is so big that the chance of you rejecting the null hypothesis is very high. Okay, so from this series of diagrams here, you are able, you can easily understand how power actually increases when your alternative shifts away from the null. Okay, the closer your alternative is to the null, the weaker your power is. In fact, when the alternative is equal to the null, then power is equal to the probability of type 1 error, which is just alpha, right? You can imagine like this distribution shifting towards, increasingly towards 0. When it goes to 0, then the rejection region is basically the same as the rejection region in the null hypothesis. Okay, so basically you have a result like this, right? So for fixed n, this is your alternative, yeah. So 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, right? So your power would actually, so at 0.5 it will be alpha, and then it will decrease. So it will increase when you get alternatives that actually go away from the null. Okay. The problem with the problem here is that we do not actually know what is the true alternative, right? Because if we knew, then there would be no point doing the experiment, right? Okay. So basically, there is actually what we call a power function. Our function would be this is the power, so this is the alternative. So this is a function of theta, right? So for, let's say in this case, so your theta is 1/2. That would be the same as your alpha. Okay, and as you move towards 1, it will basically increase this, move towards, go like this. The power, of course, the max is 1, right? So maybe the curve is something like maybe the curve is more like this. All right. So this is for, let's say n equals to 20. For different n's, you will have a different curve, yeah. Okay, because when you have a different n just now, your the distribution of your test statistic basically is still normal, but it can actually become the spread, right? Actually becomes narrower if your sample size increases, right? Remember, because it's normally distributed with this with variance equals to this function, and it's a reciprocal of n. Yeah. So when n increases, your standard error actually decreases. So then the more weight is actually concentrated at 0. Yeah. Okay. So this is the curve for n equals to 20. Right. If you have a curve that is for n equals to, let's say, 50, so the curve may actually go very rapidly like this, and then right, and so on, right? So you can have different kinds of you can have different scenarios, okay, and you can generate this curves. You can have n equals to 100, maybe it even kind of like go like this. Okay, right. So the point here is that we want to fix a power, right? We want the test to have power that is above a certain cutoff, right? So let's say 80%. Generally, in the field, people use 80%, right? But it may depend on applications. So if 80%, that means let's say it's this line, right? So you make a cut. Okay. So then you could say that. So there are two ways to look at this. One is that if you strongly believe that the alternative is a particular value, then what you do is you basically put a vertical line, and you find the sample size that actually exceeds. So let's say for you then match here, right? And match here, and then this one matches here. So this one, for this alternative, the power is actually less than 0.8, and this is a sample size of 20. Okay, so that means sample size of 20 is not going to give you a test with power of 80%. It's something lower than that, so you don't want. So you keep working your way until you basically find the sample size that actually gives you a power that exceeds 0.8 at a particular null hypothesis that you strongly believe in. Okay, that's one approach. The other approach is you set the power at 0.8, right? And then you could comment that if you have a sample size of n equals to 20, then you can only detect alternatives that are within certain intervals. Like for example, it can detect alternatives that are below, let's say, 0.3 and above 0.7, right? Okay. But it can't detect anything that's below that. But the others, they can, right? Let's say you look at the others, they can detect these alternatives. Okay. All right. So when your sample size is large enough, the range of alternatives that you can actually detect, right, will be larger, right? So as sample size increases, the range of alternatives, right, that can be detected will increase. Okay, and in fact, if you have extremely large sample size, you can basically detect very small differences, right? That and that may not be actually a good thing because, like in last week, we mentioned that issue of practical significance, right? You could detect some differences that are very small, but they are practically meaningless. And you can still get a p-value that's very small. And the reason is simply because the sample size is big enough, right? When the sample size is big enough, you can basically detect all kinds of alternatives. Okay, so this is one way to do it, right? The power analysis. Okay, you could either go by a specific alternative, which is then you do a vertical line like this, and then you decide which of the sample size is going to give you a certain kind of power, or you fix the power, right, and go across, and then you comment on what are the alternatives that are detectable under different sample size scenarios, and then you advise the client. Okay, so personally, I would think that this approach is better, right? Because generally it is very difficult to know what alternatives are reasonable. Okay, so if you go by this route, right, you go by one particular alternative, there are too many kinds of things that you need to look at, right? But rather, I think better just go a horizontal like this, and then you can consider several scenarios that are reasonable, and then you can present. Right? So this may be something that is you want to take into account. Okay. And of course, I'm talking about the theory here, right? So it's good to know the theory, right? In practice, when you actually do these calculations, we don't do it by hand, right? There are computer packages to do this, right? But you should know the theory, okay? The computer package that can be used to do sample size calculation is the PWR package. Okay, so you can actually, it's actually quite easy to use, but it has, it's not so direct that you only use the alternative parameter value. It incorporates something called effect size. Okay, so the effect size has got something to do, it's a kind of function of your difference between the alternative parameter and the null parameter, and then scaled by the variance. Right. So maybe I will share this. In Spectrum, I put up the link. Yeah. So let me see. Share the link with you. I'll basically let you try this package on your own. Yeah. So okay. New share. All right. So click on this. Okay, so you can read this documentation, power analysis in R. Can you see my screen?
Yes.
Okay. In fact, you can calculate the power for different settings, two proportion case, right? So just now I was talking about the single proportion case, right? Then ANOVA, chi-square test, general linear models, correlation test, t-test, so on, right? So they basically have a concept called effect size. And this effect size varies from test to test. So basically the effect size is defined as a certain thing, like for example for t-test, right? It's defined as the difference between the null and the alternative, okay? Let me see. No, this is mean of group one. Yeah, sure. This is the alternative, right? This is the alternative hypothesis divided by scaled by the variance, standard deviation, right? So you need to make certain assumptions about these values. So this would represent, so this effect size here would basically represent your alternative, right? So this is the numerator part is your alternative hypothesis. And so the difference between, yeah, okay, this is alternative. And then here you have an additional parameter, which is the common variance, right? Because it depends on the variance as well. Okay. So basically, then you just need to you can calculate the power by putting in different kinds of values. If you leave out the sample size, you give the so you don't need to fill up all these values, right? If you the values that you actually leave out will be the result that's returned. For example, in this case, in R, if you put in the effect size, you put in the significance level, and you put in a desired power, then it will return the sample size that the minimum sample size that you need to take, right? So that's not the sample size, but the minimum sample size. All right. You can take more than that, but that's the sample size that is minimum to achieve a power of a certain amount of power. Okay? Taking more is fine. It's just that that's the number that you need to take, the minimum number that you need to take. All right. Okay. So I'll leave you to look at this part on your own. Yeah. Okay. Later you might actually need to use this package to do the calculation for the sample size. Okay. Okay, thanks, Jake, for sharing the link. Yeah. So stop share and back to whiteboard. All right. Okay, so okay. So this is all very nice from a theoretical point of view, right? But in actual practice, things are not so straightforward. Now, you have to. That's why some. If you are just a statistics person who does not actually go out and talk to people, and then you don't listen to how experiments are run and all that, you will remain at a level, if you become a consultant, you will remain at a level that requires some kind of improvement. So a lot of people, they are very okay with these things, calculating the sample size. Let's say you calculated under some alternative, okay? So there's some alternative, and you already calculated, and then let's say for t-test, right? So the minimum sample size, let's say it's 25 per group, okay? So what are you going to tell the client? Do you recommend 25 per group? Let's say the client already supplied you with some alternative that the client strongly believes in. Fine, you just say, okay, that's your alternative. And then you do the calculation using the R package, and the package tells you that you should take at least 25. So what do you tell the client? Do you tell the client it's 25?
We'll adjust accordingly to the budget.
Okay, let's suppose, keep it simple first. Let's suppose budget is not an issue. Of course, if budget is an issue, the person can only afford 10 per group, right? Then you just have to tell the client that, well, based on this alternative that you have, you need at least 25. So if you take 10 only, you are not going to be able to reject. Your statistical test is not going to have a power of 80% that you want, right? It will be less than that. So are you okay with that or not, right? So you have to tell the client. Your client is okay, then it's his business, right? You can just tell the client, okay, so go ahead, right? Because your client doesn't really mind that the test does not reach a power of 80%. Maybe some people are actually happy that they have a power. But actually, statistical tests that have low power are pointless to carry out because let's say your statistical test has a power of 50% to detect a certain alternative. That means even if your guess of the alternative is correct, for that sample size that you use, you have only a 50% chance of rejecting the null hypothesis. Okay, that's something like tossing a coin to decide. You do this experiment, and then even though your alternative is correct, right? You only have a 50% chance to reject the null hypothesis. That's like a gamble, right? So yeah, if you are willing to continue, okay, that's fine. But if you feel like that's too much risky, then because some people, when they spend money to do the research, right, they really want the result to reject the null hypothesis, right? But sometimes if they don't take enough sample size, they cannot actually reject the null hypothesis because the test is underpowered. All right, so this is one of the things that you have to know these issues very clearly before you can advise the client. So if your theory is weak, right, you will feel not confident with advising people. Okay, so that's why the confidence of the consultant actually is derived from the person's knowledge of theory. Okay, so some people think theory is not important. It's important because it affects your confidence, right? So because all these things are calculated from theory, yeah, and that's fine. But for consulting work, we go one step ahead of theory, and this is some part that you can actually kind of pick up from this kind of course, right? It's not covered in textbooks. Okay, so when you advise a client, right, 25 per group, you should actually advise something that is maybe a bit extra. 10-20% more. You know why? So if the calculation is 25, you will advise maybe 30. Let's say for 20% more, 10% is 2.5, right? So you will actually advise 30. Why? And what's the reason?
The sample collected might not be really, I mean, it might be not representative enough of the entire population. So collect more, no harm, right?
Yeah, but you collect 10-20% won't really help if it's not representative, because unrepresentative is an issue with the mechanism that you use. So if the same mechanism you increase sample size, is all useless, because if it's causing an unrepresentative kind of situation. And what would be the reason?
To negotiate.
Negotiate?
Yeah, like so clients saying like maybe they are only affordable on 25, and yeah, so it happens that we can have 25.
Well, I think this has actually something to do with the context of the problem. Maybe you can think of some problems where if you actually take 25, real world kind of situations would actually cause at the end, it will cause some issues in your analysis where you will not actually reach 80%. What sort of issues? Anyone can offer any suggestions?
The presence of uncertainty, something like that.
Presence of uncertainty. Well, when you do sampling, there's always presence of uncertainty. So okay, so I think a lot of you cannot offer any suggestion because you may be just studying statistics or mathematics and not really having much contact with the natural sciences. Now, one of the situations that if you're doing some experiments with animals, right? Let's say your project involves animals. What can happen to the animals during the duration of the study?
It might die.
Yeah, they can die of accident. They can die of illness. You see? So the number is actually interacting. It has a real world context, you see. That's why if you have people who are doing mathematics, their mind is just very linear. You know? 25 means 25 lah. What else? No. In the real world, you have a consulting kind of session. It depends on the context, right? If your client is working with animals or some living things, these things can die during the experiment, right? For whatever reason, can die because of choking. We don't know. So in order to prevent that kind of events from disturbing your statistical design, and that's why you advise adding, let's say, a bit more, 10, 20%, if the client can afford it. Okay? So this is a reason. And if you're dealing with human beings, even worse. All right? They can drop out halfway during the study. They no longer, initially they said they want to join your study. Halfway through before complete, they just refuse to come. So you don't have data, you drop, okay? You don't, I mean, like that person can no longer be considered a reliable kind of data. And then they drop out, so you will lose your sample size. In fact, if you do human studies, you should probably have a bit more. So that because human beings are notorious for changing their minds and yeah. So with animals, maybe you can still control that. Like you try as much as possible to make the environment safe and healthy for the for your experimental units. Because at any time, sometimes there can be some outbreak of disease or whatever, and that kills or because of some carelessness of the handler, some of the experimental units actually die. So this is actually the part that you learn from doing consulting, right? I do not think someone who is just purely working with numbers and just mathematics, the technicalities, they can actually advise something like this. Okay, because they cannot see the problem with just this number is okay in the context of the calculation, but if you want to make it practically work, you have to consider the real world situations, right? So I will actually strongly encourage you're all doing the Master of Statistics now, so try to expand your horizons in some kind of domain knowledge that you're interested in, okay? And pick up things that are actually specific to that domain. This domain can be anything, right? It can be biology, it can be medicine, it can be social science, it can be finance, it can be banking, it can be trading, whatever. So you need to know something about the science of that domain, yeah? So that you can actually come up with statistical solutions, consultancy solutions that actually make sense in that domain. Because the whole point of doing this calculation is to have some practical applications, yeah? the theory itself is already known, so making these calculations is not a big deal, right? But making it actually work in a proper setting by considering all the little things that actually they're actually happening in the domain field out, that requires the statistician to actually do extra work. Okay. All right. Okay. So is that okay for everyone?
Yeah.
Okay. So I've covered the part on power analysis, and I'm going to talk about the other concept in calculating the sample size. So this concept relies on controlling margin of error. Now, so this requires, for this kind of study, you require something like this. You require a pilot study. So in the pilot study, your sample size is already, so this sample size is something preliminary, okay? Usually it will not be very large, it will be something preliminary. And let's say for the case of the proportion, right? Your 95% confidence interval for P, right? This is the proportion, right? Will be P hat plus minus 1.96 P hat 1 minus P hat over N star. So I also put the star here to indicate that these are estimates from the trial. Okay, the pilot study. Okay, now from the pilot study, you want to design a new study. So usually the pilot study maybe shows that the result is going to be quite promising, but since you didn't take enough sample size, so the amount of your margin of error, so this is your margin of error. Yeah? This whole thing here is your margin of error. This is called the margin of error. The margin of error is your critical value multiplied by the standard error of your estimate. Okay, so this is your standard error of the estimate. So that's the margin of error. If you want to design a new study with a new n, right? So I want to calculate this n, right? I need to calculate this n based on information from the pilot study. So my margin of error for this new study will be equal to P hat star 1 minus P hat star over N 1.96, right? Now I use P hat star because your P hat star is approximately equal to your P. All right. So this is our assumption. Our assumption is that the P hat in the trial more or less estimated the true P correctly. Okay, you make this assumption. So then this is actually known from the previous study, right? And we want to control it within some margin of error. So we just need to, okay, actually there's a square root. Forgot the square root. So you want to control the margin of errors to within certain amount, right? So so basically you have this thing over n. You want it to be bounded by this is your margin of error, right? So you only accept the margin of error to be bounded by some constant c. Right? That means you do not allow your margin of error to exceed c. Yeah. And therefore, you can solve this inequality. So that's easy. So your n will be larger than or equals to 1.96 squared over c squared p star 1 minus p star. Okay. All right. So your sample size, minimum sample size will be something that is larger than this value. Right. So as you can see, if your margin of error, right, if you make it very small, your sample size will be large, right? Okay. Because if your C is small, then your N will increase. This part probably you can't do anything. You cannot do anything to this part because this is the natural part of the data. Okay, this is basically the property of your data. So there's nothing much you can do about this, but you could basically play with this C square. Right? So that is the part where you can work out the sample size. That's associated with certain margin of errors. Okay. In fact, if you express your C as some kind of proportion, let's say K of P hash, right? And your K is something as a proportion of your parameter estimate, then you can simplify this formula furthermore. Okay. So yeah, so this is the second way to calculate the sample size. But so this method is actually if your client does not actually tell you that they want a power analysis, it's actually better to give them this kind of recommendation because it's actually more concrete. Okay. It's actually more concrete because you basically margin of error is something that is easier to understand than the concept of power. Power is actually a very abstract concept from hypothesis testing. So that's my personal opinion. Although both of them are statistics consultant should be able to calculate both types of information, but this is probably better, right, in terms of interpretation. If you have, so this is in the case of proportion. What if you have something like a t-test? So if you have a t-test, it will be, how would it look like? The t-test, let's say a t-test for single mean, right? So it will be, the 95% confidence interval will be K n minus 1, and this would be the standard deviation K over square root of n. Right, this is the sample standard deviation, right? So this is your margin of error. Okay, so suppose, so this is the pilot study. So I put a star here, okay. The pilot study or everything star. So this is star. Okay. So now you have a new, so this is new. Again, you have, so this is the critical value for the t distribution, yeah. So you have n minus 1 s over square root of n. So for the new one, since you want to estimate n here, right? So this one, you will assume that the s is approximately s star, right? Based on the pilot study. So here your margin of error will be equal to t 0.025 minus 1 s star square root n. And you want to control this within C, for example. All right. So then if you do this, you will get P 0.025 n minus 1 square bounded by C over S star square. Okay. Now you notice that here you cannot solve this because this is this critical value is a function of n, right? So this is a function of n that is the critical value is an integral, right? It's an area under the curve, and it depends on n. So you can't actually solve this by hand, but you can definitely solve it using R. Okay, so how would you solve this using R? Suppose so your C is known, your S is known, right? So how do you solve this using R? Anyone can tell me? How would you write the R code to solve this problem? Anyone? In this case, this is your alpha is equal to 5%. So how do I determine which n will satisfy this inequality using R? Wei Yao, how to do it?
I have no idea.
Sorry?
I have no idea.
Huh? How can I have no idea? If I give you an equality like this, so you derive this inequality, right? So you know what is C, you know what is so these two things are known already, and I want to find the n that satisfies this inequality. So how do you use R to do it? It's very simple.
Oh.
Does that give you an idea?
Is it soft AB like what Riel mentioned?
Huh? Soft?
Yeah. The soft function.
Does it work?
I thought of while loop.
While loop. Okay. So how do you do the while loop?
Iterate until the limit, since we know C square over S star square.
Okay, that's correct. Even if you don't know how to do the while loop, so in your case you say while loop, right? So you basically you are going to start with 2, 3, 4, right? It's just an increment of 1, okay? So if you go n equals to 2, you definitely you can calculate this. You can ask R to calculate this critical value for you. Then you divide by 2. So you have some value here. Then you can check it against this value, right? Check, right? You check it against this value which is known. So no, still it does not. let's say, so it exceeds. Okay, it exceeds. So it still doesn't. You will only break out of the while loop if this condition is satisfied, right? So it doesn't. So does it exceed? No, it doesn't exceed. So then it moves to the second part. Does it exceed? No. So you keep on looping, right? Until at one point it does not. Right? You already satisfy this part, right? If you continue also, it will start to not exceed. Okay, but before that, when your sample size is not big enough, it cannot exceed. You will basically cannot satisfy this inequality. Okay, so this is the value where you first encounter the. This is the value is where you first encounter that this for this particular sample size, this inequality is satisfied. Because for larger sample sizes, it will definitely going to satisfy. Okay, so then this will be the value that you return as the smallest sample size. Okay, smaller sample size where the margin of error is controlled by C. Okay, of course, if you take the sample size larger, then its margin of, so it will definitely the margin of error will definitely be smaller than C, right? But you can't take any less than this particular value. So the looping is the correct way to do it here. But even if you don't know how to do looping, okay, even if you don't know how to do looping, you can just print out all these things. You can just ask R to do a for loop and then compute all these things, and then you manually check it. All right. So I hope you learn how to use computing tools in your at this master level. Yeah. You actually, a lot of these things they are basically just common sense. It's just that in your undergrad education, you will not generally. The training here is that you are not taught to think about problems computationally. You're always taught to think about problems. You want to solve them analytically, use formula and all that. No. In fact, actually, all those solutions that you see, right, that actually has a formula. In mathematics, those kind of solutions is actually a tiny fraction of how you solve problems in mathematics. A lot of problems in mathematics are generally solved using algorithms and computational methods. Very few methods can be solved by hand with a formula closed form, right? So that's why a lot of students, when they see these kind of things, they hang, They look at this like, oh, I can't solve by hand, so too difficult. No, it's not too difficult. If you know how to think about it computationally, it's very easy to do, right? You basically just need to sub in all the values and then check. That's it, right? If you know how to write a for loop, even better, right? Because then it will, you don't have to check. You don't have to print out this table, right? You know that you can find. Okay, so this is some. That's why computing skills are very important to the consultant. You don't know how to do computing. The range of tools available to you to solve the problem will be very limited, right? Okay, so I hope this kind of like illustrates that there are some aspects of the calculation that requires you to think about it computationally. Yeah. Okay. All right. Okay. So we're 7:30 now. So let's take a break and please come back on time. Right. We'll start on time at 8. Okay. So we're going to take a break now. Just a short note to everyone. So later during the presentation session, we may not be able to record the presentation session because usually when you deal with a client's problem, usually is considered P and C. All right. So to simulate that, we are not going to make recordings when the presenter is presenting the problem. Yeah. So listen very carefully to what the person has to say, and so later after that, I will ask you to form groups to discuss the presenter's problem, and then you offer the solution. Yeah. Okay. Right. So you need to listen carefully during the presentation session because there will be no recording. All right. Okay. Excited or stressed? How's everyone feeling now?
uh, excited for having real life project, stressed for 1 week. Yeah.
Okay, so I can tell you that these are the kind of consulting work. In the real life, you actually charge money for this. Okay, you will charge by an hourly rate. To usually you have a rate, so you will bill the client a certain amount of money, right? So in the real life, we charge money, but of course at this stage you cannot charge money because you are like, in fact these kind of things don't come very often for a course like this. So it's just good for having something to challenge everyone rather than I give you some it's still data set, but it's actually more exciting if there's actually a new and a fresh problem to work on. Okay. So I think to move forward, so in fact I think I'll make this your first continuous assessment out of it. Right?
As in like a report, a presentation,
no,
or a final result?
Well, will be on the quality of this. So okay, so now I want to work out how we're going to do this, right? So you have 1 week to work on this thing. Okay, 1 week, and I'm going to divide everyone into you work in groups lah, right? But you work in groups because it's better to discuss this as a group, I think, so that everyone can chip in and contribute ideas. So first form groups. Let me see. Let's form the groups first. Yeah. Share the screen. Okay, so we got group 1, group 2, group 3, and group 4. Okay. So let me see. Do you want to form your own groups, or you let me assign?
Is it like 4 person in a group? And
Yeah, be 4 people. I think, yeah. So what do you think?
maybe ask for a voting, I guess, since like, I mean, no one is responding, right? Just vote it all, or have a. For myself, I will vote for own group, of course. Yeah.
I will go for forming the group by ourselves.
Form groups on your own. Okay, just a minute. Check a few things. Okay. How about the new students? I want to hear from the new students, because the new students, I'm afraid if we form one group, they may get left out because they don't know anyone. Owen, you have anything to say?
Hello, doctor.
Yeah.
I don't have anything to to talk.
Do you want to form your own group, or you're comfortable with me assigning?
I can't understand you clearly.
Okay. Do you prefer to form your own group, or you are fine if I just assign you to some group? If I assign you to a group, that means you will work with the team members there, or you prefer to find your own teammates?
Both are okay.
Okay, never mind. So let me see. I feel like I want to be a dictator. Okay, the reason is because to mix the mix the students with certain kind of different levels of skills, right? So otherwise, you end up certain groups will not have anything. Okay, so sorry, democracy lost today.
It's okay, doctor.
It's okay.
In some cases, it doesn't really work, all right? So I think I'll just assign, and I don't know. Do you? Let's see. 1 week. It's actually considered quite challenging for 1 week. The time.
Yeah.
Or do you prefer for this to be just kind of like an experience and not in the assessment?
It depends on how do we get evaluated, right? If let's say, I mean, like due to the time constraint, probably we might have some how do I call it? Some sort of better. I mean, because of the time constraint, so that we are like working quite fast, right? So maybe like we can get some higher marks. But of course, it's like depending on performance, then we got evaluated. That's how it got adjusted, right? I guess. Yeah.
Or maybe it will just count partially to the assessment. So maybe like a 10% for active participation. And not so much about what you get. I mean, like I don't expect you to give suggestions that are well, I would expect you to be able to give reasonable suggestions. So although these suggestions may not be what I think is the best, but as long as you make you can make those suggestions, and I'm quite happy to you know, put it as a kind of involvement kind of thing. So it's not very, it doesn't really, it depends more on your degree of participation.
I think this will be more acceptable for me. Yeah.
Same here.
Maybe something like a 10%. I mean, yeah, 10%.
Because I worry like it's like if up to 30 or 30 something.
No.
Yeah.
I won't, because it's too high.
Yeah.
This one, but I'm a bit worried also that some people are not here today, and
yeah.
so what
If
are they going to
10%
do?
is okay for me. Yeah.
Okay, so maybe okay, so let's talk about what I would expect you to talk about next week. So next week, before, so I will ask Dr. Akmarina to, the group members later I'll give you lah. Okay, so we're a bit running out of time, so I'll assign. What I will do is next week, you will first discuss the problem with me. Okay, so I'll ask each group to talk about your proposition. So we have 1.5 hours to do that, right? So the 4 groups, so 1.5 hours is 90 minutes, right? So 4 groups, so about 20 minutes each group. So you share with me what are your recommendations, okay? And after that, we kind of we actually have shorter time than that, because at the end I want to combine all the recommendations from all the 4 groups and explain it to her. Okay, so then we will appoint a class consultant to explain this to the client. All right. So of course I will help from the sidelines. But what do you think about this? So of course, because at the end we have to give something that's coherent, right? So definitely we can't have like each group giving different things to the client, because then she will get confused. So we need to first talk about it, discuss it, and then finally work out what is it that we want to tell the client, right? So then, yeah, then this is what we are going to say, all right? So I think the 1.5 hours is for that discussion, and then we do another discussion from 8 to 8:30. So we ask the client to come at 8:30. So we use 1 hour to explain that. Okay. So don't worry, I will help the person to. If you get stuck, I will definitely help you. So don't worry. But someone can volunteer to be the person to synthesize everything and then present. Okay. So if you would like to be that person, you let me know later. Yeah, you don't have to decide now. Okay. Can be good experience. Okay. So think about it, right? Okay. So it's about 9:30 already. So to follow up with this thing, so I'm going to get the slides from the doctor, and then I will put it onto Spectrum. So after that, you can actually start to do some background search on the problem. Can get the discussion going in Flock, all right? You can ask questions there, so we we will work on that. Okay. So yeah, so hopefully we can offer something to her. So as you can see, the problem actually has different dimensions, right? And you've also heard about the kind of questions that I asked her, and the kind of questions you yourself asked, right? So that turns out to be a very kind of good experience, because those are the real things that you need to do in a consulting session, which is to ask questions. To ask questions to formulate an idea about the problem, all right? So some of you may still feel very blur about the whole thing. Maybe primarily it's because the background may be too intimidating or whatever, but just take this as a learning experience, right? Because if you are ever going to work as a consultant, you cannot expect people to ask you things that you already know. Okay, there will always be things that you don't know, and if you just insist on working on problems that you know, you will miss a lot of business. Okay, so that's also how consultants, they grow in strength. They will work on problems that they may know 20%, 30%. Once they finish that project, they know more. They keep doing that for every year, year in after year, 10 years after that, they become someone who is very experienced. All right, so this is the general approach, all right? Okay, so is there anything else you want to ask?
Are we going to prepare a slide for the suggestion?
When you talk in the class before we have that, yeah, please prepare some slides. Of course, but don't spend time to tidy up the slides and all that.
Okay, understand.
Just put points there. It's just like a discussion point, because we want to work out. So my grading for this is mainly on participation.
Okay, okay.
I don't. As long as you participate actively, you should be fine.
Okay, thank you, doctor.
Unless you kind of like just say I don't know, I don't care, and all that. Otherwise, it should be fine. Okay, so you don't need to make beautiful slides or whatever. Just slides with content to put to. It can be like totally white background or whatever. We just want the ideas. Okay.
Okay.
Actually, in a real setting,
Mhm.
in fact, people actually need to write a consulting report. But in this case, I think we don't need to, because the time is very short, and I think what she really wants is that kind of she showed one example of those kind of information that would satisfy some reviewers, right?
Yeah.
So
very simple sentence.
Yeah. So, but then of course they need to have some basis lah.
Yeah.
So right. So as long as we can give something that is along that line, it's okay already.
Okay.
So yeah. So
okay. Thank you,
so
doctor.
then yeah. So then you can play around with, just to have some idea. You can play around with the PWR R package. Okay, just run through the examples there, and just get a feel of what's going on. Right? Okay.
Okay.
Right. Okay. So that's all for today. All right. So that's all. Yeah. So I'm going to stop sharing, and okay. So I'm going to end the